Shall I start?
Yeah, we all can see your screen now.
Okay. Let me start. A very good evening, everyone. It's very
wait.
honor. Oh, sorry.
Suresh, I will give an intro and then you can.
Okay. Yeah. Thanks.
Yeah, good evening, everyone. I welcome you all for this AC Tech Knowledge Series sponsored by AC Tech Alumni Association, Anna University, Chennai. Today, we have the topic is advanced process control and optimization in downstream refining sector. So we have a wonderful speaker, Mr. Suresh Shah, who is also an alumni of AC Tech. He's a BTech Chemical Engineering graduate and graduated with distinction and rank holder from Alagappa College of Technology, Anna University, Chennai in 2008. He currently works with BPCL Mumbai Refinery as a manager and specializes in advanced process control and optimization. He's a certified Aspen ICs and DMC3 user from Aspen Tech and also a certified energy auditor from National Productivity Council. He has been awarded CHT Innovation Award consecutively for 2 years for valuable contribution in refining sector for his work in online blending and advanced process control. Recently, Suresh has developed digital twin for energy intensive main regeneration units, which is one among the finalists in digital twin category of hydrocarbon processing awards in 2021. Again, I welcome you all. I thank you, Mr. Suresh, taking your valuable time to join us on this session. Now the floor is yours. Please go ahead.
Thank you so much, Ramesh. Good evening, everyone. It is very honored and privileged, to be in front of you all. I know that almost everyone from AC Tech is always in a very good position, and I take this opportunity to thank Ramesh and his team to invite me for this knowledge series. I was a part of knowledge series, listening to knowledge series, many knowledge series earlier. So being a part of it, to be presenting in one of the knowledge series, I feel very honored. So without taking much of your time, let me go into the topic. So today I'm going to present on the topic advanced process control and optimization in the refining sector. To give a brief background about me, why I've taken refining sector is after 2008, I passed out from Anna University, AC Tech Chennai. I've been in BPCL. I've been posted in BPCL through campus interview. So myself, Suresh, and there is one more Suresh from mechanical engineering joined BPCL at that point of time. We were the two people got placed in Mumbai Refinery, and both of them are still in Mumbai Refinery. We are not moved anywhere. So I began my career in first unit is blending. It's scheduling and blending, but I worked basically in blending department, where we used to do online blending, online product blending, where we receive streams from various units and make HS, diesel, petrol, ATF, and we deliver to the customers. So that was my first assignment in BPCL Mumbai Refinery. And then after 4 years, I moved to a different unit called as CCR, Continuous Catalytic Reforming Regeneration. I was in the startup. So I was a part of a project team initially. And then I was in that unit for 4 years. I saw a complete turnaround, and I was heading the turnaround team at the end of 4 years. So, and I got rich experience in CCR. Since I was in project phase, with the licensor, with interacting with the process tech people and project tech people, and it was really a fascinating experience, both startup as well as one big turnaround I could see in that. Then I moved to now currently I'm in advanced process control and optimization in BPCL Mumbai Refinery for the past 4 years. So I started in the blending section, the blend ratio control, blend property control. That was my first assignment, and then I slowly picked up APC, advanced process control. So here in Mumbai Refinery, we have both. We have two types of APC. One is Honeywell RFBCT and Aspen DMC, DMC Plus, and now DMC3. So I work in both Honeywell as well as in Aspen Tech software. And so we have progressed in such a way that we have completed almost all the units with APC. And so now we are in a position where we are looking at new digital technologies which can leverage the profit or which can help the day-to-day activities of refinery. So we are now in the process of developing digital twins, machine learning models to predict product quality. So recently, as Ramesh mentioned, I developed one of digital twin, using Aspen HYSYS and made it work real time every 1 hour that it takes in data from the process data from the plant and the model converges and throws back the data to the DCS, where APC takes action based on the simulation output. So it's a full complete integrated process where simulation takes in data and the digital twin converges, and APC is able to run the unit in a more efficient way. So we chose that unit as a starting point. Like there are parallelly many projects going on in our refinery. So one such project is amine regeneration unit. The second project is also like CDU, crude distillation unit. Also, we are very successful for both. We have 2 crude distillation units. So for both the crude distillation units, we have developed digital twins and we have integrated it with APC. So that is my journey in BPCL. And now in this presentation, I'm going to cover very basics of APC. I'm not going to go in depth, and it cites some few examples from our refinery where we could implement APC and what is the opportunities we have in APC, the field of APC, for many youngsters or who are in chemical engineering department. Okay. Moving ahead, it's a small refining, oil refining, how it happens. So 1 barrel of crude has all the components. You have starting from gas, your naphtha, your petrol, kerosene. Based on the distillation cuts, we do refining and we take all the products out from the crude oil. So this is the first basic unit of any refinery, a crude distillation unit. And this is one sample refinery configuration of BPCL. Like this is a current configuration. We have got 2 CDUs and we have got 2 trains. We call it trains. So one CDU has a cracker and there is a there is a diesel hydrosulfurization unit, and you've got a hydrogen generation unit, and there is like cracker, and we got the lobs. We are basically we have got 3 crackers, and out of which one of the cracker is hydrocracker, and we make lobs out of it. Loops is one of our product, and also we have got CCR, continuous catalytic reforming regenerator, which produces maximum of hydrogen from our refinery, and we use it for our hydrosulfurizing unit, like both DHDS, DHT, and hydrocracker, and we make the final products out of these units. It's just a basic refinery configuration of how our refinery looks. So to begin with, the process control. So before going to advanced process control, let me give a small introduction about process control, how it actually works, and how it is known to everyone. But just as a refresher, let me just explain what is happening in a process control. So there is a panel officer, there is an engineer who is sitting at the DCS giving a set value, and there is a controller where it sees the set value as well as the process value coming from the field transmitter. So these are all the numbers, like how the current in the voltage comes into the controller. So it senses the difference, the set value minus the process value. It takes that error, and this controller, based on this PID algorithm, like proportional, integral, and derivative algorithm, calculates this manipulator variable. It tries to minimize error. It's very simple as that. So its set point is entered by a panel officer. Process value is given from the field instruments, and it moves the manipulator variable. And this manipulator variable also goes as a signal, as a current signal in 420 milliamps, and finally it goes to a control valve where it operates the control valve. Like that current is converted to pressure, I2P we call, and based on that sensing element, or based on the input given by this controller, that controller take action. Once again, it goes, the feedback goes back to the controller. So it's a cyclic process. So we all know how a PID controller works. So it is the output of the PID, proportional, integral, and derivative values, is the final MV which is given by the controller. So a basic part about proportional controller is like, to reach the gain faster, we give more of a proportional band PB. And for integral values, like sometimes it overshoots, and so we give an integral value to avoid the overshoots, and we try to reach the we try to reach the steady state value sooner, as well as with the lesser bumps. And derivative we mostly use for temperature controllers, where or level controllers, where it's a derivative is being introduced in the controller, and it slows down the action. It dampens the oscillations further, and so give me a second. It dampens the oscillation, and the controller performs satisfactorily to our what is desired. So this is basic about a process control. So in a refinery, it's not one process control we have. We have got process control for almost every part of a refinery, like a flow to control level, temperature, to control pH. There are n number of controllers. If you see in this block, there are many controllers in a single unit, but the action is done by a simple controller, as I explained in the previous slide. So advanced process control, what is the definition? So going to the advanced process control, it is nothing but a supervisory control deployed in some like fast computers, like within servers. It identifies the important independent and dependent process variables. I'll explain what are the dependent and independent process variables. And it also identifies a dynamic relationship between the variables that we call as models. So first of all, we identify variables which are dependent and which are independent, and we develop a matrix which is called as model, and that model works based on it's a math-based control and optimization algorithms to control the multiple variables, like both the dependent and independent variables simultaneously. So with a very layman example, how advanced process control works. If you see, there is a tub. There is a tub where there is 3 different types of water: water from corporation, water from borewell, water from hot water from geyser, and there is a temperature measurement you have. So our objective is to maintain the temperature and to maintain the level according to the requirement, and finally the optimization. Consume either bore water or the corporation water according to the prices. It's just a practical example. Like this is getting translated to refinery applications as well. So the simple bathtub experiment, bathtub example, what I'm trying to say is, first of all, we are trying to control. So what is the thing is which we are trying to control? Temperature and level. And we call this, sorry. Yeah. And we call this temperature and level as the dependent variables, whereas the water from MMC or water from the borewell and hot water from geyser, they are the manipulator variables or the independent variables. So we make a matrix, like when 1 unit of 1 ton of 1 meter cube of water from corporation increases, what will be the increase in level and what will be the change in the temperature. So we make a matrix out of it. Finally, we solve the matrix every 1 minute and we execute the process. So that is how a simple advanced process control works. So it's a very basic example. And going ahead, so what APC does is it takes the operator limit. So operator limit is nothing but the low and high limit set by panel officers. It takes the current measurement. So whatever measurement which we have in this from the panel. And there is a model, APC model, which is working at the background. It takes all this and gives the best controller set point combination for the process. So it is helping to minimize the errors, and it is using both linear program or quadratic program to find the best solution for this matrix. So phenomena, the control phenomena is very simple. Control variable, what is to be controlled? For example, in the bathtub example, temperature and level are the variables which need to be controlled. Manipulator variables, the handles to control. So there, in the example, we could see the water from the corporation, water from the hot water from geyser, and there is a water from borewell. There were the manipulator variables or the handles to control, and disturbance variable like ambient temperature or a disturbance from an upstream unit, which the CV cannot affects the CV, but there is no handle. So they are the disturbance variables for the process. It's a system, so we got a manipulator and disturbance variable at the input of the system, and based on that, control variable reacts, and based on the control variable, whatever desired number which we need, we manipulate a manipulator variable once again so that we bring back the system to the normalcy. So explaining what are the dependent, so there are 2 types of independent variables for any APC advanced process control. One is manipulator variable, the other one is a feed forward or a disturbance variable. So manipulator variables are nothing but the input that causes a change in the process, and the operator can manipulate or it can change. In that example, he can change the water from borewell and water from corporation and also hot water from geyser, but he cannot control that ambient temperature. So example, the set point to regulatory controllers, valve positions are the manipulator variables. Which with respect to feed forward variable, they also have an impact to the process, but we cannot control it. So it creates a disturbance in the process and not controllable. Example, feed flow. Like if a feed is coming from a different unit and going to this downstream unit, so that is a feed forward or a disturbance variable, which affects the process, but you cannot control it. But you can use this manipulator variable as a tool to control that disturbance caused by the feed forward variable. So finally, the control variables are the dependent variables. These values are the result from the independent variables, which the operator tries to control. Like if you see any operation or any process, the main important parameters which an engineer would like to control, like product quality, temperature, pressures, differential pressure. Some may be constraints, and some may be some of the with constraints like reactor temperature, reactor bridge wall temperature, arch temperature, furnace skin temperature. There may be the constraints where we cannot violate those constraints, and optimization parameters like product quality, like product yield. So those things. So those are the examples of control variables. So let me explain a very small with a very small example how independent variable works. For example, in this case, if you first see this wall is an independent variable. This is a handle which this process can be controlled. It's a first step. So now we are promoting that independence to this flow controller. Now we have a sensing element. The sensing element based on the flow set point I'm giving, this wall I'm opening it or closing it, and that independence is promoted to the flow controller. Now the valve is dependent, whereas this flow controller is an independent variable. Now moving ahead, I'm introducing one more variable like this. There is a temperature controller. So there is a temperature that is controlling the flow. That flow is controlling this one. So it's indirectly independence is promoted to the temperature controller, which controls the temperature or which is the required parameter for the engineer to control for the product quality or product yield or whatever it is. So based on that, this control is shifted to temperature controller, and this flow controller is a slave, and further its slave is this valve. And I'm also introducing one more variable, one more independent variable, which is the cooling water temperature or the ambient temperature. It's a feed forward disturbance variable. So some basic definitions about before we go in detail about APC. So one is time to steady state, and one is a unit response time. So these are the two basic fundamentals which you start any APC project you will need to know. So one is the time taken to see, like time to steady state is nothing but time taken to see the full effect of the dependent variable when the independent variable is moved from time t now. For example, I'm moving this independent variable, which is MV1, a unit like for 1 ton or 1 meter cube per hour or 1 meter per second. So what is the effect on the control variable, and when that effect is completely realized? So when it is reaching the steady state. So that time to steady state is a very important parameter to be noted for any APC model. Then comes the unit response curve. So unit response curve is nothing but, so whatever unit change I'm going to give to this independent variable, what is the response on this control variable? Whether it is when I'm changing this by 1 meter cube per hour, this is going to increase by 0.5 degrees Celsius or 0.01 degrees Celsius, or if it is a flow, if it is increasing by 0.3 meter cube per hour, whatever it is. So what is the effect of this unit change in the manipulator variable over the dependent variable, over the control variable? That is the unit response curve. So when you assemble all these curves together, you form a matrix like this. This is one simple example for one fractionator column where a normal engineer can control only one set point at a time. Like steam to reboiler, he can adjust manually. He can either control top cut quality or the side cut raw temperature or the side cut quality or the reboiler outlet temperature. He cannot control all together. But in an APC model, when you give this as a matrix, when you give this as an input to the APC model, when you just give the set point or the limits, low and high limits for these variables, and low and high limits for these control variables, and low and high limits for these independent variables, APC by the matrix or APC with the model at the background controls, and it pushes the unit to the profit. So without lesser intervention from the engineers, the plant will run to a steady state. Like first of all, the plant will be controlled, but this involves a lot of understanding of the process first, and then about the software, and then your experience in like we call it as a step testing activity, and how do you tune the basic PID controllers at the DCS level. So it is having a lot of things in the background, but once if it is done, it gives a very it makes a plan very smooth, so that the panel officer enjoys working with APC. So we can see normally, even when I joined this department, I always had the feeling like the panel officer, even when I was in the process, when I was working using the APC, so I always had the process, I do better than APC engine. But only when I moved to the APC department, I could understand that no. So it is whatever I understood was not wrong, was not right. APC does a better job. Whatever we can't see, whatever the predictions or whatever the quality parameters which I can't see, which I can't take every 1 minute, I cannot be sitting at the panel and doing action every 1 minute. Whereas APC, just within the limits or within the using this matrix, it is able to push the plant to a very steady state, also to a very optimum state. So that is the beauty of advanced process control. So I'll just explain few more examples of refinery cases of how we use this APC to increase our refinery profits. So how APC helps our daily refinery operations. So it maximizes profitability by maintaining 100% uptime, like optimal operating conditions, 100% time. It increases the unit intake, so you can push the plant to the maximum. You can give the constraints. You don't hit the constraint, but whenever there is opportunity, go to the feed, go to the maximum feed. That is always possible through APC. You can reduce energy consumption. Sorry, in the earlier example, you can see that we had both steam reboiling as well as reflux flow. But what is the optimum? Either to increase steam or to optimize on reflux. We, as a normal engineer, cannot do that in real time, do a calculation and come out of the number. But if APC model is working at the background, it can reduce the energy consumption. It's not even steam, like fuel gas firing, your furnace firing, your steam temperature, you are seeing all your constraints and pushing your product to the quality, like not within the away from the limits. It is not making your product off grade, but at the same time, it is using the minimum energy required for making an on grade product. So it reduces energy and also it maximizes productivity. If you have, for example, a crude distillation column, if you your profitable components are the diesel components or the petrol MS components, petrol components or the LPG components. So the distillation, the APC can push your model, push your plant in such a way that all this profit-making products will be increased. The yield of these profit-making products will increase, whereas the lesser profit-making products like your residue, your yield, so residue yield, your gas made, so those things can be minimized using the APC strategies, but it is bounded by the constraints. APC solves complex refinery problems. It is by interacting between the process variables, understanding the process constraints, and also it improves the process economics. So it pushes the plant to optimal constraints. For example, if you see in this case, so it's a boundary. APC works, the advanced process control works within this boundary. So there is a pressure limit, there is a temperature limit, there is a quality limit, there is a flue gas limit, there is a delta P limit. But a normal operator may be operating in this zone. Like he will be honoring all the constraints. He will be operating in some zone here. But the APC knows what is the true economic optimum and pushes to that point. So which a normal operator or normal engineer cannot see in reality. So with APC, without APC, when you just start a plant, you always know there is a bumps, the plant is not steady, you are like there is fluctuation with temperature, pressure. But I'm not saying even with APC, there may be fluctuation, but if you sit in the with the engineer, you understand the problem, we can really come out of the solution, come out of this problem by tuning the DCS level controls and improving the process controls so that we pushes the limit. So without APC, though the plant behaves erratically, with APC, first of all, the first process, what APC does is first it controls. It controls the process and then it pushes the process to the maximum, like to the profit margin. So that is how an APC works, and that is how it maximizes refinery profits. So I'm going to explain two examples. One is a refinery example of CCR, continuous catalytic reforming, and the other one is diesel hydrotreater. First, I'm going to talk about continuous catalytic reforming and regeneration. What are the APC strategies we have currently in place, and how are we leveraging it to our maximum profits? it's a simple PFD of a CCR unit. So where we got reactors in series. So the reactions, we all know that reforming reactions are endothermic. So we have a heater in between the reactors to bring the temperature back to the reactor temperature of around 515 to 563. After the reactor, it goes to a plate type exchanger, and then it recovers maximum heat out of it, where the feed is preheated using the fourth reactor outlet, and it goes to a separator, and from separator the gas is getting circulated back to this reactor section, and part of the gas is taken out as called as HP compressor or high pressure compressor. So this gas and this liquid are brought in contact with at this high pressure absorber, where this bottom liquid is pumped at a high pressure and the gas is compressed to a high pressure, like from normally say from 2 to 35 kg. The liquid is also pumped from 2 to 35 kg, and it is brought into a contactor. Where in this contactor, we by mass transfer, we are trying to improve remove the lighters from the gas phase to the liquid phase, and the heaviest from the liquid phase to the gas phase, and then it goes to a chiller, and then it goes to hydrogen. Because in the reforming reaction, you always generate hydrogen. So we have a PSA, pressure swing adsorption unit, and there's a chloride garment because the catalyst has some chloride. So it is poison to the downstream unit. So you've got a chloride guard absorber, and the hydrogen, pure hydrogen of almost 99.9% purity comes out of this section. And the second part, the liquid section, goes to this LPG absorber, where maximum LPG is recovered. Then goes to a stabilizer, where stabilizer removes the further lighters going to the splitter column. So stabilizer removes LPG and the lighters fuel gas, and the bottom goes to the feed to the splitter column. The splitter column, some units has a splitter column, some units don't. So you have the splitter column where you split that reformate into 3 cuts: top, middle, and heavy. We have got an aromatics recovery unit. So we use our middle reformate, which is rich in benzene, toluene, and xylene for our aromatics recovery unit. And we use a light reformate and heavy reformate. Heavy reformate is the one which is rich in RON, research octane number, which is very important component for making petrol. So our main objective is to convert the naphtha, which is of a lower octane number, to make it to a reformate with a higher octane number. And the byproduct, which is hydrogen, it's one of the important byproducts which we get from this unit, which is used further in the units like DHDS or DHT or downstream units. Also, this unit as a this is always a profit-making unit like CCR. So pushing the yield, as I already said, pushing the yield when the benzene demand is high, when the toluene demand is high, maximizing middle reformate. When the MS demand is high, maximizing heavy reformate. And hydrogen is always a product coming out of this unit. So optimizing this unit is very important for the refinery margin. So here, so these are the various sections we have got in this unit, and we have implemented APC in almost all the units. So in the first section, our main objective is a research octane number. Like as I already said, it's one of the important component for making gasoline. So we may maximize RON by optimizing the reactor temperature. We also increase the octane barrel by optimizing the reactor temperature. And we have this hydrogen to hydrocarbon ratio, because the recycled gas which is getting circulated through the reactor section, if you spend more energy, you're heating the gas once again. So where we spend more energy, and we're also spending more energy in recycling it. So we, in both the cases, we will get good profit if you optimize this hydrogen to hydrocarbon ratio within the desired limit. If you're going less, your coke formation will be more, so that is not desired. But if you're going high, the problem is that it acts as a heat sink, as well as you are using more steam for the recycled gas circulation. So we get profit on both. We get it's a profitable to run in a very optimized way. Then coke, we in CCR you make coke. It's a continuous regeneration. So you make coke on the catalyst. How to control the activity, like how to move the catalyst from one reactor to second reactor, and how to optimize oxygen in the coke bed, because you cannot put more oxygen; it will lead to a runaway reaction. Will damage your regenerator. How to avoid such damage and control your process. That is a big challenge which we have in this process. In fact, we have patented this APC in CCR section because this was one of its kind, where we, for catalyst transfer as well as for coke burning, we adopted some unique approach for using APC and hydrogen purity, like maximizing hydrogen out of PSA. Though it is a side product, so maximizing hydrogen will always help in the refinery in real time. And it's one simple animation of the second column, like stabilizer and splitter column. So how did we do? What is the benefit we got? So as I already said, there is a feed coming, that's a liquid after all the hydrogen is getting removed. The liquid which is rich in LP, now the liquid has LPG, it has reformate, it has got gas. So what we do, so there is a LPG absorber drum. So it goes to the LPG absorber drum, and from there it goes to stabilizer. So stabilizer, the bottom is heated and the top goes to the reflux, and we remove LPG out of it. The LPG, we remove it from the top section. And the gas is once again, because the gas still has some LPG content, so we once again recirculate it back to the LPG absorber. From the bottom, it goes to the second section called a splitter. So where the splitter pressure is controlled, and we remove these three cuts: light reformate, middle reformate, and heavy reformate. So what we did is, like, we did this control, like deboiler outlet temperature control, tray 20-way temperature control, and LPG absorber pressure control, and splitter pressure control. These are all the handles which I took in APC. So took in control. So these are the control valves which are actually there in the field. We took these controls, and with the help of these APC strategies, we could reduce the flaring. So before APC implementation, we often observe flaring from the splitter column, and we are continuously being questioned why such flaring is happening from refinery, and how to avoid that. So we could come out with some innovative approach, and we could adopt all these, integrating all these variables put together. We could reduce flaring from the splitter column almost 8%. It's almost nil now. So we are post APC implementation case, we finalize the benefits, almost 8% reduction in the flaring from splitter column, irrespective of any feed composition. Though the feed composition varies, the problem was with the feed composition. The feed is becoming lighter to this column, there was more flaring. The feed becoming heavier, there was no flaring, but the LPG was getting disturbed. The product LPG was getting disturbed. So those things we took care using APC strategy, and we could come out of an excellent strategy which will help in reducing flaring, also made on-grid LPG. So apart from this, for all other sections, we could achieve some benefits, like in NHT, 1 to 2 tons of fuel gas, like based on the product sulfur. We got a sulfur analyzer at the outlet. Seeing the sulfur analyzer, NHT reactor temperature is adjusted automatically by APC, and we could achieve some saving. In CCR, I already said we could improve the reformate yield, heavy reformate yield to 2.2 to 3%, and so that octane barrel also increased almost 3%. And then CCR, 35 tons of fuel gas reduction, either both by flaring and then like optimizing the reactor temperature based on the desired octane. Because if you put more reactor temperature, if you increase the reactor temperature, what happens in CCR is it goes to cracking mode. Instead of reform, heat does cracking, and you lose more heavy like the rich reformate. Instead of making reformate, you make LPG. So this we optimize the fuel gas composition, not the fuel gas composition. It's optimizing the fuel gas firing in the furnace. We optimize the reactor temperature so that whatever RON we could achieve, that was the RON was targeted, and at the same time we could reach the desired octane as well as the desired products like heavy reformate yield. We could optimize on fuel gas savings, and also the bed temperatures, the region bed temperatures. We could reduce the standard deviation of, like as I already said, APC first does the process control and then optimization. So it controls the product bed temperatures. It almost 80% reduction in standard deviation we could achieve using APC. So now going back to the second unit, which is a diesel hydrotreater unit. So here I will explain what is the strategy which we adopted for APC. So if you see, there are two sections. So it's a reactor. So there are two temperatures. One is a reactor inlet temperature, and one is first bed inlet temperature, and this second bed inlet temperature. So what we do is, our ultimate objective is to control sulfur. So optimizing both these temperatures, we need to obtain sulfur. And these temperatures are dependent on the firing. So when I increase this temperature, it increases the firing on the furnace. And when I reduce it, it reduces the firing. So what APC does is, like, I have given these as my manipulator variables, both the reactor. We'll just see this example first. So reactor temperature as my independent variables are the manipulator variables, and the product sulfurs, and there are a list of variables like skin temperature, WBT, first delta. Like these are the constraints apart from the sulfur. So apart from product sulfur, I've given some constraints also. You don't violate these constraints. At the same time, make me a good product, like make my product of quality with a lesser energy. So what APC does, so once it reaches the desired limit, for example, if you see in this case, the current value is 4.34, but whereas the high limit is 5. So though I'm not able to zoom and see, yeah, so it is 5, whereas the current value is 4.34. So APC is telling to reduce the reactor temperature of first bed, whereas the second bed is increasing to maintain the delta T. So it is reducing the reactor temperature so that, which in turn affects your furnace, like firing, reduce your firing in the furnace, and you make a product quality of, like, with the minimum giveaway. Like I'm not making a product with too much of quality giveaway, as well as I'm optimizing my fuel firing in the fuel gas firing in the furnace. So this is what the reduction in the furnace firing. So how APC engine works? So it's nothing but there is a box. So it does three things. One is prediction, second is steady state optimization, third is dynamic control. So plant operator, who's the plant engineer, enters the limits and targets. So he enters a low and high limits for independent and dependent variables, and also the targets, like sulfur target is this much, my SOx emission target is this much. So he enters the target from the DCS, and it goes. And apart from that, we also introduce some cost. We say that firing fuel gas is costly, so don't use it to a lesser extent. Whereas feed it to be maximized, so it is a positive or negative number. So we introduce cost to the variable, and the APC admin like us, we also have some tuning constants, like tuning parameters like move suppression, max move, or steady state value, or steady state SS move limit, or the cost factors like LP cost. So we give these tuning constants. So APC engine takes all these as inputs, and it gives the move or CV values. Like what are the current values? Like we, as I explained in the process control example, like one variable based on the difference between set value and process value, the controller is giving a set point. Controller is giving a manipulator, like wall opening. Similarly, this APC model, and taking all these as inputs, it understands the process and it gives a set point to this DCS through the DCS through OPC. It gives set point or output values to the DCS. So first it predicts, like it understands how the value will move in the future when I increase this reactor temperature by 1 degree Celsius, and then it goes to the steady state optimization, where it takes the data from the DCS, what is the manipulator variable, current variables. Sorry, and it gives MV targets and CV targets for this dynamic control, and this dynamic control gives set points to DCS. And this entire cycle happens every 1 minute, and this controls the entire process unit. Every 1 minute, it gives set point and reaches a steady state, and also optimizes the process. So DCS set point is entered, limits are entered by the panel officer. There is a dynamic APC admin is entering the max move suppression, and all these input goes to the dynamic control. And APC, I already shown a matrix, which is nothing but a APC model. It predicts it predicts what will be the CV moves or the independent variables future moves. It goes to a steady state optimization engine, and then it goes to a dynamic control engine, and finally it gives a point to the DCS. So this entire process happens every 1 minute, and it optimizes the process. To give a brief about evolution of how APCs evolved, like this was how the controllers were earlier with the complex wires. Even now there are complex wires running in the background, but which you don't see, and they were all pneumatic. So people go into the panel just adjusting the pneumatic controls and taking actions. Was the first DCS pictures. And 1989, our refinery had a privilege of using the, like Charles Cutler, you all know he's a father of advanced process control. He first started a company called Setpoint, so which was then acquired by AspenTech later and became DMC or DMC3. But we had an opportunity there. Like I did not have an opportunity. My seniors who were in APC or who were earlier in this section, they worked with Charles Cutler, and they could do the first APC implementation in our refinery. It was for a cracking unit. So we had a first-hand experience of how to work with APC initially. And now we have moved, like first, it's just an example of Yokogawa system. We have moved from like traditional machines where people used to use pencil and paper to advanced latest computing technology. And we don't, like now engineer don't sit with the pencil and paper. He uses all the softwares available to him to make this process control work perfectly. Going back, so my next topic will be the inferential quality prediction of soft sensor, which are being used in refinery. Why we need inferential prediction of soft sensor? There are many reasons for it. The main reason is like you have many products, like starting from fuel gas, LPG, motor spirit, gasoline, diesel, or furnace oil, bitumen, coke, whatever it is, whatever product, and all products have got different specifications to get certified in lab. So if you need to have analyzers for all these products, you will require almost from 10,000, or if based on the refinery size, you can even require almost 1 lakh analyzers for a refinery, which is completely impossible even. And also the costs of maintaining these analyzers and AMC to maintain these analyzers are also very costly. What the inferential or soft sensors does is it takes the process data, it takes the lab result, it combines both, it develops a model, and we does all of the soft sensor. It is simple, robust, and adaptable. So what is the process of inferential building? So we first take the data. So in any refinery or any process unit, only 3 data is available. One is flow, pressure, and temperature. To use all these 3 components, and you have the lab results. We take some 100 samples or 60 samples or 70 samples. We're combining both these, the process data and the lab result, we make a math model. It may be either statistics, it may be fuzzy logic, or now currently using neural networks, and we make the final product quality prediction. So what are the inferential qualities we have in refining? For sulfur, flash point, freeze point, RON, distillation, percentage purity, RVP, apparent H2S and amide. For all these qualities, currently we have soft sensors. So research octane number, one example. So what are the various temperature, what are the various parameters we take for research octane number is? Like in our case, we take this reactor temperature profile based on all the reactors, delta T across the reactors, then hydrogen to hydrocarbon ratio, and a splitter column condition, which is the final column where the reformate comes out. And we combining all these, we make up inferential, and this is how the inferential predicts with lab. So it's almost matching lab. So it avoids usage of an analyzer. It reduces the analyzer requirement. Similarly, for RON, we can also make inferential for any quality parameter. So it increases, which helped in, like if there is a quality parameter available in real time, I can optimize. I can use it in APC. I can use it in advanced process control and increase the CCR HR RON. I can absorb more naphtha, because I already said HR is an important, heavy reformant is an important component for gasoline. More the RON and more the naphtha absorption, and we could achieve almost 5 lakh per day by using this inferential prediction. Now coming to splitter bottom IBP prediction, like this is a feed to continuous catalytic reformer. So heavier the feed to CCR, the more the heavy reformate generation. So predicting this quality was very important. Was for CCR when we did this project. So we could predict the quality of distillation cut. So this is one of the examples where we could measure or predict the distillation cut of a feed to CCR, and it's how the value matches with the lab result. Product diesel flash prediction. You all know flash is one of the important safety code of any product. Lower the flash, higher the risk of product handling. So meeting minimum flash point while naphtha, because you can absorb naphtha if you know the flash of your diesel, you can put more naphtha. And so for flash, what we do is we optimize steam in a stripper, but when we optimize steam, if there is a H2S carryover, that will cause copper corrosion. So we need to consider in totality, not only flash point, also on copper corrosion, also on the wild naphtha absorption, and finally reduce the steam consumption. So if you have a real-time measurement available, you can do all these things. You can reduce the quality giveaway in HS. So future. So what is the current projects which we are currently undergoing? Since, as I already said, we almost covered the entire unit with APC. So almost all 100% of the process units in the refinery is covered with APC. So we are even conferred like some Frost and Sullivan Digital Awards. So we were APC, 100% APC implementation refinery was one of the important criteria for assessing the digital preparedness or the digital way where our refinery is well ahead of our peers. So now after implementing APC, what is the next step? So now we are in the process of developing digital twins. So how do we do it? So here in our case, we for a CDU model, I'm just explaining how we have done that. So we take the crude type, crude quality. We have got a patented product called as BP mark. So we take density, sulfur, viscosity, and MCRT of any crude oil, and we can characterize that crude assay. So we can have the quality parameter of the crude as well as the product coming out of that using that product with software, and that is fed to a simulation model because the BP mark product works in like a steady state, like for 1 atmospheric pressure. It's called standard pressure conditions, whereas simulation model takes the absolute plant conditions, the absolute temperature, pressure of a column. So it goes to APC console. The output is mainly quality parameters or the yield, which is maximum, which can come out of this crude. So it goes to the console, and APC in real time sees this, and there is an online interface where both the model is scheduled to run. It takes the process data for running, and also it throws back the result. And APC, based on these inputs, it takes action and pushes the refinery to maximum profit. So since crude is the first point of any refinery, so pushing the unit to the profit margin is one of the important criteria, and we do that in real time now. So for both the crude units, in our case, in our refinery, we have this digital twin running very successfully, and we have integrated it with APC as well. So we could get a potential benefit of, it's very marginal, but still it's real time. We are able to sense this benefit based on the various crudes we are being processed. And now the case which we were conferred for one of the finalists for hydrocarbon processing award is for this amine treatment unit. So amine treatment or amine regeneration unit, whatever you call. So so what happening in the process is there is an amine regenerator. Where amine is used in refinery is like in any refinery, amine is being used to absorb H2S. So H2S is generated from the sulfur. So crude sulfur which is there, it goes to as different cuts, different products like diesel hydro treating unit, or a diesel hydrosulfurization unit, gasoline treatment unit, or VGO treating unit. Wherever we treat sulfur, it becomes H2S. Like we use hydrogen to convert sulfur as H2S, and that H2S needs to be absorbed. We use amine. What we do with this amine which is rich in H2S, we put this in a regenerator. We put steam. We take out the acid gas. You take this acid gas to your downstream sulfur recovery or tail gas treatment unit, where you remove maximum sulfur out of it, and the rest you incinerate it and send it to atmosphere. And what happened earlier is, because we were put a challenge, or we have put a question like how to optimize steam for varying crude sulfur. When your crude sulfur varies, are you optimizing steam in real time? That was a question put forward by our top management, and we came out with the answer like no. So what we could do is we can optimize steam in amine regenerator units based on the crude sulfur. So how it affects us, like when the crude sulfur is increased or decreased, your downstream process units like DHDS, DHT, hydrocracker, there also your amine absorption or amine H2S absorbed in the amine increase or decrease. First, what we did is we optimized the amine circulation. So the usage of amine itself we reduced based on the feed sulfur. So with that, we could reduce the feed to these units. First, that was the first point. And then when these amine rich in H2S is coming to this unit, comes to this unit. So what we did is, how can we optimize steam so that the apparent H2S or the lean amine which is coming out of this process is always okay for the, like it is recycled back to the amine absorber unit. So how well we can measure this apparent H2S in lean amine. So that was a challenge, and that we could answer using digital twin. So we developed simulation models for the amine regenerator units. We first validated the simulated models with process data, and these validated models were deployed online using Aspen Online. And using real-time pressure, flow, temperature, and feed quality, we could predict the H2S, and we could also use this prediction for the APC where advanced process control optimizes the steam to these regenerating units based on the estimates from this coming out of this unit. So this is one of the one case where we developed recently, and we could achieve a good steam savings of almost around 50 to 70 tons per day in real time. And it not only predicts apparent estimates, it also predicts the acid gas generation, which is helpful from a downstream unit like sulfur recovery or sulfur TG2 tail gas treatment to make, like, because sulfur recovery unit are a bit tricky. If you don't know the composition at the upstream, you will end up either making black sulfur or your choke your SRU condensers. So this information is very much essential for the downstream units. That also we can provide. Apart from that, we can do some significant steam savings in this unit. And finally, before I conclude, I would like to see, I see some opportunities in this field, which new chemical engineers or upcoming chemical engineers can always look after. First of all, we don't have an indigenous APC engine or a PID tuning software. So as of now, even if it is there, we are not licensed it, or we are not using it as a standard product. So any process engineer can work on it. We can develop an indigenous APC engine, because we are spending crores of rupees and dollars for this APC licenses from foreign vendors, which we can avoid if we can make indigenous APC engine. Also, PID tuning software, which is for any process units, this PID tuning software always comes handy, and they can use it to their full potential. It will always have a market till the refining sector or till the process sector is there. PID tuning software and APC engine will always have life. So that is one part. And secondly, we don't also have service providers for existing APC software for both new projects as well as maintenance. Like some companies like Honeywell have their own engineers, but some companies like AspenTech uses the ISPs, service providers, for execution as well as maintaining. We in India, we find it lesser number. So there is opportunity for people to work in that area, to be a service provider for the existing software, and they can grab new projects where we can work together. And like, if you always see the difference between a licensor giving you a support and a service provider giving you a support. So with the cost factor involved, you can have a very good and there is a very good scope with the service providers if it all there. And finally, the buzzwords like artificial intelligence, deep learning. So imbibing those things to process control will always help in the future. So that's it from my side. Yeah, thank you. I'm open to questions, and thanks for everyone for patience with me.
Thank you, Suresh. So it's a wonderful session. Really appreciating. It's one of the complex topic. You made it really simple. Okay, so I think there are a lot of questions coming up. So I will ask the participants to unmute themselves and ask questions directly to you, please.
Okay.
Vaibhav, it seems like you got few questions. Can you go ahead?
Yes, sir. Like I've posted it in the chat box.
Okay, you want me to?
No, sir.
You,
like I'll read it to him, sir.
Yeah. Could you introduce yourself briefly, and you can ask the questions?
So let me, like, my name is Vaibhav. I am currently doing my 4th year in like instrumentation control. I'm from like NIT Trichy.
Okay.
I got to know about this from one of my friends' parents.
Okay.
So it was like really insightful question. So thanks a lot.
Okay.
So yeah, I had a few questions. So first thing was, can you talk about the like brief algorithm that is being used for the APCs?
APCs, the algorithms are like the advanced process control algorithms. Like everyone have a different set of software, but it is simple matrix where if I've not covered those things in detail, so it's a matrix between the dependent and independent variables. You solve a matrix and you get a solution. So they accept set points based on the limits we set, and it in simple, if you ask me, it's just a matrix. It solves matrix every 1 minute and it gives you a steady state solution. So that is how it works. And yeah,
is it like similar to like linear quadratic, like regulator?
Yes. It's something like that. Yeah.
Okay. Second thing was for the system identification, like for system modeling, do you use the like black box modeling, or do you use any other method? That is, like you get the input output data and then you model the system for the APC model?
Yes. Yeah, the APC model is based on the input-output data. So what we do is before building any APC model, we do a step test. That is the terminology we call. So what we do is we do a change or a step change for every variable. Whatever. First of all, we identify what are the dependent variables, what are my independent variables, and I do a step test. I vary the set points, I decrease the set points. I do both increase in direction and decrease in direction, at least for 10 to 12 steps for a variable, and identify the response of the dependent variables. So based on the response, I do a matrix. They're all first order. Most of them are first order response only, and we take the process gain which is coming out of every variables. When I increase one of the variable or decrease one of the variable, what is the response of the dependent variable? We make a matrix out of it. So for that, similarly, we do for all the variables, whatever variables we identified as dependent and independent. So we do step testing for all the variables.